Okay, welcome back. So in this session we will have two talks. The first one by Paul Heslop from Durham, talking about the Correlahedron. Yeah, please.
Okay, thank you very much, and thanks to all the organisers for this wonderful workshop. I've been having a great time here. I decided to do a Blackboard talk, which means I hope to be pedagogical, but I'll probably neither be pedagogical nor get through what I want to say, but we'll see. So this is one of the hedrons that we spoke about at the start of last week. So to begin with, the plan is very simple. I'm going to talk about correlators, and then I'm going to talk about geometry. And much of this... Oh, okay. It's had enough already. Much of my work on this was done sort of in 2016, 2017, but there's been some recent work, mainly by Song He and Yuten Huang and students of theirs recently, that's sort of given some new life to this and some new calculations. So I'll talk a bit about the old stuff, a bit about the new stuff, maybe try and connect the two together a bit at the end. First of all, let me give a bit of motivation for what we're talking about. So I'm going to talk about correlators or correlation functions in everybody's favorite planar n equals 4 super Yang-Mills. So the features of these are that in a CFT, which n equals 4 super Yang is a CFT, then correlation functions of gauge invariant operators are the key ingredients, really, that you first think of. They're almost essentially what define a CFT, correlators of local operators. And in particular, these are the subjects of, you've heard about conformal bootstraps and things. That's what they're bootstrapping, these correlators. The correlation functions have a primary role in ADS-CFT. So the basic example of ADS-CFT is n equals 4 super Yang-Mills with 2B string theory. And the basic objects there are the correlators that I will be talking about, and they are dual to graviton amplitudes in an ADS5 space. It's related to integrability, which I won't talk about at all, but there's a lot of fascinating work there. And probably of main interest here is that they give amplitudes. Okay, so they give amplitudes in two different ways. This ADS-CFT gives amplitudes at strong coupling, string theory amplitudes in 10 dimensions. But in a much more mundane way, they give amplitudes via a light-light limit. And these are the normal amplitudes that we've been talking about today and last week. So in other words, the amplitudes in n equals 4, planar n equals 4 super Yang-Mills, flat 4D space. Okay, another thing that occurred to me, I added this after Yara's talk, reminded me to say, they are infrared finite. So once you've found these integrands, I mean, the integrals are difficult, but they are finite. So there's no need to worry about epsilons and things or any other sorts of regularizations. And they're the most precisely known, okay, I have to be careful what I say here, at least at the integrand level. So many people would say, okay, they're not precisely known, but as far as integrands are concerned, they're the most precisely known objects in the theory. And in fact, it's from the correlators that we get the most precisely known amplitudes. So for example, at 4 points, which, as we'll see, 4 points is equivalent to what I'll kind of call MHV, but I'll explain what I mean by this shortly. Well, until recently, this was known to 10 loops. So 4 points was known to 10 loops. And then last year, or this year, no, last year, I guess, Sung Hee and his, I guess, mainly students in Beijing, did 11 loops. And in a recent paper the other day, he was promising 12 loops. This is future work with Jake and Sung and Xi and Tang. This is promised. Okay. I mean, this we did in 2000 and I think it was 2016, and we thought that was. I mean, there's a spectacular number of even just fitting it on a computer is difficult. So I don't don't know how much disk space you need for these. Okay, so these are the correlators in 4 points, but these imply actually via this light limit that you therefore know the 4-point amplitude as well. You get it very directly to this many loops. I won't say much about this, but basically these are given by certain graphs, and you can take squares within these graphs, and they give you the 4-point amplitude. Similarly, you can get the 5-point amplitude to one loop less. So this would be 9 loops, 10 loops, and 11 loops. If when we have these, you can very easily get the parity even part. But in fact, you can also get the parity odd. You then reduce a further loop down to get the full 5-point amplitude. And you can even get 6-point amplitudes. At least this is sort of conjectural, but at 6 and 7 points, 1 and 2 loops from the 4-point correlator, you can get 6-point MHV and NMHV and N squared MHV amplitudes from that. Again, you reduce a loop. Another loop there. Not so direct. These are very direct. To get 6 points, at least the way we did it, was to write an ansatz of the then take anything that's points is n. The number of L's is k. And then it's at L loops, so you're looking at G to the L. G is the 't coupling. Okay, so this is, I am sort of, it's going a bit beyond amplitudes here, so if you're not really familiar with the super amplitude, it's going to be tough, but it's analogous to an n to the k MHV amplitude. We just heard about this. So you can think of these as your positive helicity gluons, and these are your negative helicity gluons in some sense, right? And they, just as the negative helicity gluons sit at eta to the 4, these sit at theta to the 4. So actually, this is this plus SUSY related. So this is kind of like me writing down a gluon amplitude, but then I want all the SUSY related stuff, which I do in superspace. So actually, I just consider this in superspace, and I'm looking at theta to the 4k and g to the L. Okay, just like super amplitudes. Yep. Yeah. But here it starts. Here it starts the supermultiplier. So in the on-shell superspace, it's in the middle, but here it really starts. And it's squared, right? These are all products. This is this is a stress tensor multiplier. It has products of fields in. Okay, so now so far it looks very analogous to an amplitude, ANKL. But before I go further and talk about that, let me say that, in fact, we can write the following. GNKL is equal to GN plus L, K plus L, 0, if I switch off or look at theta n plus 1 to the 4 up to theta n plus L to the 4. And the reason for this is just sort of fairly basic quantum field theory. A higher loop, when we compute one loop correlators, what we effectively do is bring down the interacting Lagrangian into the correlator. And here we're looking at correlators involving Lagrangians. So loop level means more Lagrangians. So if you look at this, here I've got n plus L objects, and I'm at k plus L. What I've basically done is I've brought down L Lagrangians into the L further Lagrangians. So I've got, it looks a bit like that, plus k Lagrangians plus L Lagrangians. But, and now I can look at that at tree level instead. Okay, so in all the same family, so compared to amplitudes, there's nothing like this for amplitudes. It's telling me that a tree-level amplitude or a tree-level correlator contains within it a loop-level correlator. Okay, so that's a very nice thing to have in mind. Okay, so now let me look at the light-light limit. And then it really does give me amplitudes. Or more precisely, it gives me the square of amplitudes. So very, very precise, well, not very precisely, but a little bit more precisely. Correlator, if I send xi plus 1 squared to 0, for all n points, then I get a squared n k L. So the next question is, what is a squared? And what you do there is you take the super amplitude and square it, and then take the corresponding term. So this is really sum of products of amplitudes. Okay, so e.g. a squared, let me just do 4 points, 2 loops. What do? I take the full amplitude, 1 plus a 1 plus a2. Okay, I only need those terms. If I square that, I get 1 plus 2, whatever I get. At order g squared, I'm going to get 2a2 plus a1 squared. Okay, so that's what 2 loop is. I guess I should put my g in for this to make sense. Okay, so, and I get more and more products. That's what this is giving me. Okay, but I've also got this relation here. So what do these two things together imply? They tell me that if I take a correlator of 4 plus L points and L, so, well, I'm using this notation now. This contains within it G4, 0, L. It also contains several other things. I basically can peel off the Lagrangians one by one. So it contains G5, 1, L minus 1, etc. This arrow means that they contain with it in the sense that I gave over there. I take particular theta terms in here, I can get the terms down here. Now I take the light limit. So I can take a 4-point light limit, and I get I want to draw the arrow all from here, because this is somehow like the master correlator. The 4-point light limit, and I get A for A squared at 4 points at L loops. Or I can take a 5-point limit at L minus 1 loops, and so on and so forth. I can get all of these things in one go. So this would be A squared at 4 plus L loops, K equals L, and tree level. The single correlator has all of these different amplitudes contained within it. And that's kind of also what I was referring to here. And this is only the 4-point. This is only really the 4-point correlator. I can also consider G5, 0, L and have a similar story. Get more amplitudes. So there's different things I want to say here. That the 4-point correlator by itself contains lots of amplitudes, and there's an extent to which you can extract individual amplitudes from this square. So that was the point I was making way over there. But then there are also higher point correlators which can give you more directly different amplitudes. Okay, is that clear? That's the end of the introduction to the correlator. So now I move on to geometry. Are there any questions at that point?
I have a question. Do you know if the coefficients of the IR divergence of the amplitude is somehow easily encoded in the correlator? The gamma cusp that Johannes also discussed, other than like going to the amplitude and calculate, regulate it, and so on, in some finite operation, if you can extract it.
Yeah, that is known. So there was a paper. Well, it was that instigated this light limit correlator amplitude correspondence by Maldacena, Alday, and Burkhardt, Eden, and Sokachev. And they, yeah, the gamma cusp. So I mean, you can just look at, for example, the 4 points. The light limit there, 4 points has 2 cross ratios, U and V. And the light limit corresponds to them both going to 0. Okay, so you've got a finite object, the correlator is finite, but now I want to look at the light limit to go to the amplitude, corresponds to taking this finite thing and sending u and v to 0. And you get a log u, log v type of divergence. And that gets multiplied by gamma cusp. But then you also get, unfortunately, these higher type of divergence with various coefficients here. So this is the only one that has a log u and a log v, but you get high powers of individual log u's and log v's. And these coefficients are a little bit confusing, difficult to understand. But that term does isolate for you gamma cusp. It's yeah, I mean, I remember your stories looked very similar to this. Okay, so geometry. So you're supposed to recall something that I don't believe you've actually been told yet. I was kind of hoping that you would have been told this. So this is the Amplituhedron in the ATT form. So this is Nima, Arkani-Hamed, Yara, and Hugh Thomas. So they gave what's the right word? A form of the Amplituhedron which didn't rely on a C projection. It was directly in Amplituhedron space. Okay, and the Amplituhedron looked like this. ANKL equals, it's a bunch of Y's. Okay, the Y's are K planes in K plus 4 dimensions, as we've seen. Then we also have, if we're doing loops, we also have some 2 planes. As Yara was saying, they're often written as AB in K plus 4 dimensions. And then they satisfy various inequalities. So they have a Y, I plus 1, J plus 1 inequality. They have a Y, I plus 1, AB inequality. And then they have a Y with 2 loop variables, so AB, I, ABJ inequality. Okay, and we know hopefully what these brackets are by now. So these are all K plus, this is a K plus 4 by K plus 4 determinant here. Okay, and then they also have these flipping number rules. 1, 2, 3, I has K flips. That means as I runs from 4 to N, the sign changes. So this can be positive and negative, but it changes K times as you go from 1 to N. And then there's a loop version as well, a loop flipping. Maybe I don't need to write that down. It's something like Y, A, B, I has K plus 2 flips, I think. Okay, so that is the Amplituhedron. And I think it's still a conjecture that that's equivalent to the original definition that we've heard of, so the C.Z version where you have a positive C. Okay, and now if you cross out the last 2 bits, it turns out that you get this thing is equal to the square of the Amplituhedron. A squared NKL. Okay, and you can make this statement more refined. You can change the number of flips. So I think this is the maximum number of flips you can have, but you can have fewer flips. And these give you the products. So in some sense, this, if I get rid of these things, I've got a union of a bunch of geometries which are kind of joined on lower codimension things, and each one is giving me a product of amplitudes, and they sum up precisely in the form of, you know, that example product I gave over there. So this is the square, this is geometrically the square of the amplitude, which is what we want to get when we take this light limit. Okay, there's a few things I could say here, like, so it's a union of geometries, and there was a bit of confusion at the start about this union of geometries, but it's really the union that you inherit from the background embedding space.
Paul?
Yep.
Can I ask, maybe, I think you kind of said it, but maybe just for my understanding, I'm slightly confused about the degree of a form. So in the first definition, we have the canonical form, which is the integrand.
Yes.
And then you said that we get the amplitude squared, crossing out these two conditions. So naively, I would have expected we get something of the same degree, same type of form. But
yes.
I think you just said something about that. Now, it seems like there's an extra prescription of taking why to take these products. So maybe I think I missed something there.
Yeah,
just not naively, I would have expected to get something of the same, you know, form.
So
of the same
they will all have the same degree. That's a good point. So I can do an example with, maybe there's a better example is with different k. If I consider a case of higher k, then I will get things like ak plus ak minus 1 a1, ak minus 2 ak. So this is NMHV degree. And it turns out that the forms, you know, the product of these two has the same, always has the same
Thank
degree.
you. Yeah, I should have thought of all of these combined. I see. Okay. Thanks so much.
No, good question. Thanks. Yeah, I just wanted to talk, maybe I won't write anything down, but the in this union, it didn't quite tie in with the original definition of positive geometry. And actually, there are the positive geometry defined by Lam and Nima Arkani-Hamed requires every maximal residue to be 1. And that doesn't happen here. And this worried us for a long time. But in the end, I think there's a natural definition of positive geometry, which is just that inherited from the background space. And then later on, we realized that the two-loop amplitude has the same issue, or a very similar issue. Two-loop amplitude also has maximal residues that aren't 1. So it's not a positive geometry in the original sense. It just requires a slight extension of your definition of positive geometry. Okay, that was an aside comment. So, what is the Correlahedron then? So this is kind of, I'm trying to work towards or motivate the definition of the Correlahedron. So this was the thing we conjectured back in 2017. So this was, again, it's for GNK0 because the others are just projections of this. So it's the set of y's in GR n plus k, comma n plus k plus 4. And then we just have this single unified bracket. So it's, I mean, it's conceptually very, very simple. Of course, it's also very big. So I have this n plus k here. So actually working things out with it is very difficult, but conceptually it's very nice. So you can kind of maybe imagine how in the light limit, it reduces to this. I mean, let me draw a picture just to illustrate things. So a correlator is a bunch, actually I should tell you what this depends on. What are the x's? So this is, its correlator depends on x's. And these are two planes. These are elements of 2, n plus k plus 4. Whereas here, this thing depends on z's, well, and also the AB planes. I mentioned those, I guess. Z is in a GR1, k plus 4, I guess. Okay, so that's the sort of the background data, and then I've got a y that has some inequality depending on those xi's and xj's. But so the x, I've got a bunch of x's, and these are lines in twistor space, and they don't know about each other. They're just going around randomly. So that's the correlator G. But if I take a light limit, what happens is these guys are intersecting. Although actually we tend to think of it as the y touching them in a certain way, but for a certain projection they're intersecting. Some of them are intersecting, and then some of them are left over. And this then becomes the tree level amplitude, and this becomes the AB lines. So in other words, this becomes Z1, Z2, Z3. And these become AB1, AB2, AB3. Okay, so you get that's just a picture to show you how you get from the correlator picture to the amplitude picture. Hope that's clearish. And you can, geometrically, you do this by a freeze and project. Freeze Y to lie on this, xi plus 1 equals 0, and then you project. Okay, I won't go through the details, but it's geometrically what you're doing here. And geometrically, this thing reduces to that squared amplituhedron. Okay, and then we did a few checks. To be fair, most of our checks were at the level of the squared amplituhedron rather than the correlator itself. Again, because the correlator is so big, it's difficult to do checks. So we checked the squared amplituhedron, and since then we've done more proofs at the level of the squared amplituhedron. This thing here. Right, 10 minutes. What can I say? So one of our checks was 4.1 loop, except that by 4.1 loop, we are always thinking of 5 points k equals 1, so kind of like NMHV. It's always the MHV bar case that corresponds to the 4 point. And now, let me write something down. So this is a y. It's in GR 6, 10. Okay, so that's just that in this case. GR 6, 10. So let me try and write down a y. The x's here are a 10 by 10 matrix. And so we set it to the identity. And then my y, I can set, so the symmetry is GL6, but I also want to impose a GL2 to the power of 5 because of the x's are planes, and I have this GL2 symmetry at 5 x's. Okay, so what I do is I write something like this down. Using this symmetry, I can set my matrix to be of this form. A, B, C, D. Okay, then I just plug in the inequalities, y, xi, xj. These are now just 6 by 6 minors. The xi and xj's are set to the identity. So this is just 6 by 6 minors. I'm saying that's bigger than 0. I get a bunch of inequalities in these variables. I then use something called cylindrical decomposition, which is in Mathematica. You just literally type in, well, the best thing to do is generic cylindrical decomposition, and then you put in your inequalities, and you give it an order of your variables, x, x bar, a, b, c, d. I'm sure they don't want me to be writing underneath the screen, but anyway. And then it gives you an answer in a form which you can immediately work out the canonical form of. Oh, actually, if you really want to do this, you also need to put 1 at the end. It gives the various dimensional terms. Okay, so what it's doing for you, it's slicing up. You've got some region given me by inequalities. Cylindrical decomposition slices it up in the way that you would do if you were trying to integrate a region, and you wanted to slice it up into a dx dy integration. Right? You slice it that way, and then you slice it that way, and so on. And then you can read off immediately what the canonical form is. Okay, good. So that was the situation back then. So, and sorry, let me give you the answer. So the answer is a form in those variables, and then you need to uplift it to a covariant form. Uplift the result to covariant form. So let me show you what it actually looks like. It's going to look like, well, I can't find it, but it's x1, x2, x3, x4, x5, a 10 bracket. We're in GR 6, 10. We have 10 brackets. Then I have the y's, GR 6, 10. The natural form is like this. And then I simply have the product of all the xi, xj's. And you can check that all the weights then match perfectly. Okay, so that was the check we did. So that was so that is G5, 1, 0. And that was really working. That's the correct answer. That is what we want from the correlator in this Amplituhedron language. It's essentially just equivalent to a graph like that. These terms here are the kind of these things are universal, and then this is the key bit, which is given by these graphs 1, 2, 3, 4, 5. Okay. Now, if you wanted to go to 2 loops, then Mathematica fails. At least, well, I mean, I don't know how long you wait until you decide it's failing. I don't know how long it's going to take. It took longer than I was prepared to wait. And so the thing remained like this until a few months ago, this paper by Song and Songhee, Yutin Huang, and Kai, and they have managed to do G5. Well, in their language actually, G411 loop. Sorry, 401 loop. That's the one we just did. They've done 2 loops and 3 loops. They also work. This is something I kind of thought was never really going to happen, but The new ingredient, oh, there we go, is the concept of chambers. And they kind of slice your tree level, They kind of do this cylindrical decomposition for you. They do the slice into tree level in continuous bits, continuous chambers. And they were able to, well, partly using that and partly using other things, get the 2 and 3 loop. Now, what I wanted to say is they do it in a slightly different way. Maybe I can just write a formula down quickly. They write, so it looks like they're doing things slightly differently, but in fact it's the same. Operationally, they have the same variables, the same inequalities. They uplift it to a slightly different object, and it's because they're really thinking of these guys instead of G620 and so on. Well, if anyone's interested, I can show you how to go from one to the other. There's another projection you can do to go from the form in GRn plus k, n plus k plus 4 to their form. And then the other thing I don't have time for was to look at this thing, G50 loop. So this guy is much less well known. People are computing it at the moment and have computed it. And it would be really interesting to try and get it from a geometry. We have a geometry. The modding out by GL2 is not so clear, but actually, if you go to the twistor space formulation, then I think the modding out by GL2 becomes clear, and there's a way of attacking this. Sorry, I did promise at the start that I was going to be neither pedagogical nor finished, so I succeeded in that. Thank you.
Thank you very much. Questions for Paul? Comments? Johannes, is there a microphone around?
So, do you know if there is any progress in terms of understanding either the Correlahedron or the Amplituhedron squared from a Grassmannian point of view, as like the image of the Grassmannian? Is that something that people have tried? Is it possible?
we did look at that. We did do that for the squared Amplituhedron. Yeah, it's kind of like there's a C, you stack 2 C's on top of each other. Actually, maybe not for the squared, actually, but for the products, where you have a definite number of flips, but fewer flips than the Amplituhedron itself. So the Amplituhedron has a C matrix. These product ones have 2 C matrices, where I forget the conditions. The top C matrix is maximum ions. The other one is, I forget. I can show you. But it's very naturally sliced in the way that you want to take 2 C matrices from 2 amplitudes and stack them together, basically.
All right, thanks.
Questions? Johannes.
Nice talk. I'm curious, there's these other correlators. So here you discussed the ones with the stress tensor multiplet.
Yes.
I think there's this other interesting object where one combines trace of phi to the something with different somethings.
Yes.
And yeah, I'm just curious if you have any thoughts of those objects. Could there be some positive geometry?
No, that's great. Well, in some sense, that's a wonderful new feature. So that was right at the end of my talk. So as you say, you literally just add them together. Trace phi squared plus trace phi cubed plus trace phi to the 4. Okay, if you have the right dependence and you have the right normalization, you can naturally think of that as one object. And like forgetting about the geometry for a moment, this story here, in Minkowski space, this is just xi minus xj squared. And this becomes xij squared minus yij squared. You have these extra y variables that are looking after the phi's. And that gives you the same function, doing that simple replacement, and then expand it out, it gives you the whole thing. So in some sense, like, at least operationally, you've already got the full answer now because of that. Now the question is whether you can really think of this this is really 10-dimensional variables though, and a lot of the story is pretty 4-dimensional. So, another question is at higher points, at 5 points, it's not known what the analog of this simple, this is for 4 points. You actually take these F graphs, you probably know what they are, and just replace that. Higher points, it looks more complicated at the moment, but the idea would be that it's super invariant times functions where you do this replacement and you get the whole thing in one go. So yeah, geometrically, I'm not sure. It's an interesting question.
Right, thank you. Yeah, so operationally, there's already this 10D symmetry conjecture that gives it,
yes.
but it's a bit strange, would be satisfying to find a geometric
exactly.
underpinning.
Yeah, very much so.
Thank you.
One more question. So this geometry gives the whole square of the amplitude, which contains several pieces in it, right? So do you think it's possible to impose additional conditions, not the ones for the amplitude, some other conditions, and get one of the pieces separately, not the whole sum? Can you do you think you can divide the amplitude square space?
Yeah, that's what I was trying to say. So if you just change the number of flips.
Right, but but it gives the product in the end.
Yes.
Right, yeah. So do you think there is a connection back to the amplitudes? Because somehow we are dealing with products and amplitudes versus the amplitude. The geometries are not the same, but they kind of live in the same space.
Right. So you want to take one of these things with the flipping number that's non-maximal.
Yes.
And then you want to try and understand if I can somehow...
Some map to your space, basically. Start with the two spaces for the Amplituhedron itself. Some sort of projection or map into your space. I don't know how to, I don't a priori know how to do it. But the fact that they, in the end, have the same differential form.
Yeah, I don't know. I can repeat what I said about there is a C-matrix picture that we have where we stack the C matrices together on top of each other.
Yeah.
And the sort of on-shell diagram type picture kind of goes through.
So it will have to be understood. Yeah.
So maybe thinking about
quality language. Okay. Any more questions for Paul? If not, thanks a lot again.
Thank you. So